Hello, my name's Alicia Hatmaker, and my course project is titled Can I Shower Before the Food Gets Here? Um, After my girlfriend and I run out of groceries, we often rely on food delivery services for a couple of weeks before we end up going shopping again. And my girlfriend always wants to know if I think she has enough time to shower before the food arrives. So I use this project to help me better answer that question for her. So the main objective of this project is to understand the variables that influence food delivery and to develop an accurate predictive model to help estimate those delivery times. And some of the questions that I'll be looking at are which variables have the strongest relationship with delivery time, and on that same token, which variables don't have significant impact on the time. For example, is the driver quality more important than external factors like weather and traffic? And finally, which predictive model provides the highest accuracy or lowest error? This dataset was posted by Gaurav Malik on Kaggle. The primary data source is the train.csv file from his food delivery dataset. And the dataset's from a machine learning competition conducted by HackerEarth. So I think this is kind of like a manufactured dataset, but it has about 45,000 observations. The main response variable is delivery time in minutes. And some of the predictor variables are driver attributes like age, driver rating, their vehicle condition, latitude and longitude of the restaurant and the delivery locations, the order details, date, time, type of order, which means like, did you get snack, drinks, full meal, and external factors like weather conditions, traffic, festivals, and city type, which basically just means urban or metropolitan area. And then delivery logistics, such as type of vehicle, whether it's a car or a scooter, and number of additional orders that the driver completed at the same time. Before I started building any models, I did have to clean the data. I removed irrelevant variables like ID numbers, removed observations with NAs and location coordinates. And I assumed that some of the coordinates had the incorrect sign because when I looked them up, they were in like the middle of the ocean. So I just flipped the sign on those, cleaned some text columns, converted variables to factors, converted dates and times, and then I also created two new variables, one to tell us which day of the week the delivery occurred on, and a variable to calculate the distance between the restaurant and the delivery locations. So after all that cleaning, we ended up with about 38,000 observations and 12 predictor variables. First, we did some basic data exploration. Here on the left, we have a summary of the variables involved. You can see driver age ranges from 20 to almost 40. Ratings range from 2.5 to 5 with an average of about 4.6. You can also see the counts for the different categorical variables. There's pretty even spread amongst most of these variables, except for city type, where 77% of the observations are from metropolitan areas compared to urban. And then we also have the distance variable, which ranges from 0.9 to 13 miles with an average of about 6 miles between the restaurant and the delivery location. And then if you look at the histogram on the right, you can see the delivery times range from around 10 minutes up to an hour, with the majority of observations falling within the 15 to 35-minute range. And then here we have a few plots to show how some of the variables are distributed in relation to delivery time. So if we look at the top box plots, we have traffic status on the left and weather conditions on the right. We can see that low traffic and sunny conditions both have the quickest delivery times. And then if we look at the violin plots on the bottom, on the left, we can see that orders where the driver completed 2 or 3 additional deliveries had significantly longer delivery times than orders with just 1 or 2. And finally, on the bottom right, we see that drivers rated under 4.0 all took over 30 minutes to deliver the food. and those rated between 4 and 4.5 had higher delivery times than those with ratings over 4.5. And then here I just did a basic linear regression for quantitative variables to see what their correlations were with the delivery time. So as you can see, they all have pretty similar correlations. The number of deliveries was the most highly correlated with 0.38. And then the only negative correlation was the rating, which means that as the delivery person rating increases, that the delivery time is going to decrease. So to better understand delivery time, I applied several different predictive techniques, including ordinary least squares regression, and then I used the k-fold cross-validation and regularization methods within that, and looked at lasso, ridge, and elastic net models. I looked at single decision trees and aggregate tree models for both classification and regression scenarios, including random forest and bagging, and then it did a neural network model for regression. So the main method with all of these techniques is going to be splitting the data set into 70% training and 30% testing, and then building the different models using the training data, evaluating variable importance along the way, and then predicting the test data, and eventually evaluating the model performance using error measures for regression, and then accuracy, misclassification, sensitivity, and specificity for classification. So we first looked at the OLS regression with the different regularization methods applied. These regularization methods are used to address overfitting and improve accuracy. And so we used the 3 different methods: lasso, ridge, and elastic net. Also used the k-fold cross-validation resampling method to assess how the model developed by the training data will perform with new test data. So as you can see from the table on the right, the models all performed very similarly. But the lasso and elastic net models narrowly had the smallest error and highest R-square, indicating they were the best performing. And then if you look on the left, the OLS model found that driver ratings was the most important variable, with the number of deliveries, weather, traffic, and delivery distance being the other major variables. And again, I also wanted to look at this from a classification perspective. So I converted the delivery time variable to a yes or no. Yes meaning my girlfriend had time to shower, and no meaning she didn't. So any deliveries that took over 30 minutes were converted to a yes, and the rest were converted to no. So in the top right corner, we have the confusion matrix from our actual data. And there was enough time to shower in 11,697 of the 38,000 observations, or about 30.73%, which makes the benchmark accuracy for this test the 69.27%. So after running the logistic model several times and removing insignificant variables, it ended up taking out the order type, day of the week, vehicle type, and order time. And then looking at the coefficients of the model, driver age, number of deliveries, and delivery distance show that as those variables increase, the rate by which the odds of having time to shower increases, while holding the other predictors constant. And then the opposite is true for driver rating. So as the rating increases, the odds of having time to shower decrease, or the food arrives quicker. And then on the right-hand side, you can see the receiver operating curve is well above the benchmark, and the area under the curve is 0.9431, both indicating very good model performance. And then you can also see that the accuracy was 87.83%. Then I looked at tree-based models for both classification and regression. So the actual tree is too complex and large to show here, but we did run the single decision tree, random forest, and bagging models. and then compared the accuracy, misclassification, sensitivity, and specificity of them all. So the best performing model was random forest with an accuracy of about 94%. And then if you look at the left, delivery person rating was again found to be the most important variable, with distance, delivery distance, traffic, number of deliveries, and weather falling behind that. Then we did the same thing here for the regression trees, where we did the single tree, random forest, and bagging models. And random forest again produced the smallest error and the highest R-square, meaning that it was the best performing. The variable importance did kind of switch around a little bit compared to the classification tree. The delivery driver ratings was still the most important, but traffic and weather seemed to be more important in this model than the distance between the restaurant and the delivery location. And this regression tree model also brought the driver age into the variable importance model. For neural networks, I only looked at the regression instance. I did try to run it a couple times for classification, but I had trouble getting it to converge, and it was just taking so long to run each time that the potential increase in accuracy just wasn't worth the benefit for this situation. So before running the neural network model, I converted all the variables to numeric and normalized the data using the max-min normalization method. And then I ran a few different neural network models using different numbers of hidden layers and nodes. And the model that I found yielding the lowest error had one hidden layer with 5 nodes, and is shown in the plot below. And that model resulted in a very small mean square error and an R-square of 0.556. So after running all the different models, I wanted to compare them here using error and accuracy measures. So on the left, looking at the classification models, they all perform better than the benchmark accuracy, which was 69%, indicating they can all be useful models. The random forest model had the highest overall accuracy and lowest misclassification, meaning it was the best. As far as the regression models go, they all performed well. Rounding kind of cut it off here in this slide, but the random forest model had the highest R-square. The neural network model had the lowest error, but the complexity of the model and the time that it takes to run aren't necessarily worth the small decrease in error for this situation. In conclusion, whether or not you want to use a classification model or regression model to look at food delivery time really depends on your own personal needs. I prefer to use a regression model when assessing delivery time to get a more specific time frame rather than a simple yes, you have time or no, you don't. But regardless which way you look at it, I'd recommend using the random forest models. And then as far as the variables affecting delivery time go, driver rating was by far the most important, impacting delivery time in all of the different models. And then traffic, weather, delivery distance, and the number of deliveries completed were the other important variables. And then the type of order, so however much food you order, the city type, vehicle type, those were not important. And the day of the week was not a significant predictor either. So I guess I didn't really need to go through the effort of creating that extra variable, but those are the types of things you learn when you're evaluating different types of models like this. So I appreciate the topics that we covered in this class and just want to say thank you so much for a wonderful semester.